All right, am I on? Okay, let's get going. So thank you all very much for coming today. Like the slide says, my name is AlbertMitchell. I've been working at Cisco for 23 years. I have been doing technical marketing work for over a decade. First, I was in the Catalyst team. Now I'm in like the industrial Internet of Things, industrial switching, industrial routing. So this presentation is definitely going to have an industrial component to it because that's the business unit that I work with, and the customers I work with directly are all purchasing industrial products to solve problems that they have in various industrial type deployments. So what we're going to do today is the problem as I see it, as it gets presented to me when I consult with customers. What are they trying to solve? What is it? So then we have a solution with our industrialized products. I'm going to explain that, how to deploy it, okay? How to troubleshoot it, and then we're going to wrap it up. If we have some extra time and somebody actually has a couple problems, I would love to try and solve them for you while we have time. I think everybody would benefit from that if there was actual use case somewhere. So I asked a couple people, but no one volunteered one, which is fine. So what are we actually trying to do? So this is, as it gets presented to me, this is really kind of the problem that we see. There are machines that are pre-built, and I'm using these robots here as an example of a pre-built machine. So you buy a robot, and in the robot, it's got a very sophisticated communication inside, okay? And they're using IP addressing inside this machine or this robot, and they're making lots of these robots, and they don't use any dynamic addressing, right? You buy a robot, right? You get the software for that robot, and internally they're communicating with all the various components to move, things like that, shift, hydraulics. They're probably using layer 3 IP addressing and static IP addresses internally, right? And they're doing it on purpose, right? It's easier for the robot manufacturer. I don't want to pick on the robot manufacturers, but a lot of machine builders do it. If you were buying a diaper making machine, right? The diaper making machine has components in it with software that uses IP addressing. Every diaper making machine has the same IP addresses, right? And it always comes as this packaged solution. This is what you get, right? So they're doing it on purpose, and what we're seeing is now with the digitization, now we want to get more data out of these machines. Now we actually have to sort of get into these machines and pull the data out. But that's one use case, but you may also find other cases where you're now having to sort of connect to these devices where they've got duplicate machines. So what we're seeing is they have sophisticated networks. What they come with most of the time from the manufacturer of the machine is one device is dual NICed. So you talk to that one device, and that device sort of represents the entire machine. It's obviously some sort of controller of something for that machine, and that's what you would traditionally communicate with, right? And so there's no outside communication with the components inside the machine. If you only have to communicate with the controller in the machine, then you don't really have a problem because the controller has a unique public IP address, okay? And so the alternative to what we're about to show, and this is what I see a lot of, is if you have to get into the internal components of the machine, you obviously have to put another layer 3 device. It's either a firewall or a small router or some purpose-built, NAT, PAT type translation device, and you have to put that from the machine into your public network, and you have to add that. And this is, for a lot of people, this works. They've been doing this a long time. It's just one more device you have to manage. Typically, when we get into these kinds of networks, we're not dealing with engineers who are sophisticated when it comes to IT or networking. They often know very little about it. And so having to maintain now a firewall or a router deep within their network, like at the machine layer, is a really tough thing for them to have to deal with, right? So this is essentially the problem that we have. And so what we have on the industrial networking is a feature called Layer 2 NAT. And I want to get to you the reason why we're calling it Layer 2, but sort of keep these things in mind. Layer 2 NAT works at Layer 2, so it's not routing. We have it on our industrial switching products, so it's working at Ethernet layer at Layer 2. It does not do 1 for n, it's 1 for 1. So you keep that in mind when you're trying to determine the unique public IP addressing. You can't just have 1, you need 1 for every device you want to translate for. And it does not do layer 4 port addressing. It will work at line rate. It's an Ethernet switch, works at line rate, both ways, bidirectionally. So if something's coming in from the public with a public IP address, it comes into the switch, it gets hit, gets translated, comes back out private, and versa versa. One of the things we're going to use a lot of these terms, public and private. Public is always referring to the public side where you have to have a unique IP address, and the private side is referring to something inside the machine where it would be duplicated from one machine to the next. One of the things that you need, what we often see is we have to fix up ICMP and ARP. These are the only 2 IP packets where we go into the payload to find the internal IP addressing and translate them there as well. Because if you're doing ping or ICMP or ARPing, the IP addressing is also in the payload itself. So we will fix those up. And we're also talking, I'm going to keep using the same IP addressing, the 10 network and the 192 network throughout the rest of this presentation, but it can be any layer 4 IP address. And the way that we're doing it internally, and this is how it works, and you'll see later on, that we have a switching component. It's just whatever layer 2 switching ASIC that we have, could be a Doppler-based ASIC or something else. But we also have a piece of hardware that does the translation. And this hardware is associated only with specific interfaces. Okay? So when we are doing this, we can only translate, say, on the uplinks or only on specific downlinks or something like that. And it's going to be different for different IE switching models. So read the data sheets carefully or the configuration guides carefully for whichever IE switching model you're using. The interfaces that are available for translating on will change. But the idea here is pretty simple. So because the switching ASIC is different than the translation component, all the forwarding decisions are made irregardless of the translation. So the translation doesn't know anything about forwarding. Forwarding doesn't even know it's being translated. Separate deals, not talking to each other. No context is shared between these 2 components. Okay? So let's take a very simple use case. We're back to our machine. And what we're trying to in our use case is we have some sort of data collection device. So now we need more data about what's happening in the machine to increase efficiency. This is a sort of standard digitization use case we see. So we have now device, and I need to communicate with my HMI machine device component within this machine. So I am going to pull out my first CLI command here. So again, sorry for those, but this is iOS. We're going to use CLI commands. It's just easier to explain things. The network administrator would define the translation, and he would come up with the unique public IP address, and in the switch, he would say, this is the translation. So internally, it's 192.168.1.3, and we're going to translate this to 10.0.0.99, and that is unique within the public routable space. Okay? And now we've also defined with this where the architecture change is going to be. We now need within the switch itself has to think about public and private, right? And we need to add a link now because we're not going through the controller anymore because the controller's not doing this for us. The controller is not a layer 2 bridge. It's not bridging or routing between the public and private. It's got 2 separate NICs that it's not doing any switching or routing for us. So now the machine needs to connect to an IE switch, which will do it for it. And it will switch between, and now it has to exist between the public and the private. All right, so this is now a different way of looking at it. So we've got our HMI device over on the right. We have our layer 2 NAT switch. And below that is the configuration that we're going to use. So now we have, one of the things we do with the translation is we're going to define this layer 2 NAT instance, right? HMI machine 1. And we're going to show permit all and fix up all. We'll get into what those mean in a second. But most critically, the HMI machine needs to find its gateway. So if I'm going to communicate with that collection device that's in a different subnet, I need to have a gateway. It will already have been configured typically with the .1 of its subnet. And it needs to find that. And so we're going to have to translate that because that is actually on the zone layer switch in the public. So we're going to have to translate the gateway's IP address as well as the IP address of the machine itself. And so what you're looking at now is it's going in both directions. So we're saying outside, so this is the public, it's coming from the outside in this device, coming from the outside in, so it's coming to this one, and we're calling it a gateway so that when you look at the configuration, you can notice it. And then we have an inside device from the private coming from this particular host, and we're going to translate it to this uniquely public IP address. And now we're going to apply it. So here's our machine. We're going to apply it to this uplink interface here coming out of the switch. And we're going to say only look and try and translate things on VLAN 3004. So it is VLAN aware. So here's the layer 2 NAT part of it, right? I haven't changed VLANs, right? So it's the same VLAN. I'm making a layer 2 forwarding decision, and I'm going to translate the IP addresses in both directions. Sure.
What does the IP switch do to prevent the spread of broadcasts between different segments?
Machines?
Which are all connected to the same VLAN?
Hold that thought. We are getting there. Yes, you've already caught the next problem. Let's get everybody in the room on the same level here in terms of how this actually works, and then we'll show that, okay, now more of a real world scenario, how can we actually solve it when I've got 10 machines, all with the same IP addresses, all in the same VLAN. Yep, how can we solve that? We will get there. So what I'd like to show is, so in this particular case, my app collection device is sitting out here somewhere in the network. It's directly or indirectly connected to the zone switch. That's not really that important. But pay attention to the colors, the MAC addresses, and the IP addresses as they are relevant because we are making a layer 2 forwarding decision. So you'll notice when it leaves the gateway, the destination and source MAC addresses don't change as it goes through the NAT, right? It's a layer 2 decision. The MAC addresses don't change. All we've done is change in this case, we don't change because we don't have a rule for the data collection app to translate. We don't translate that, right? So it stays 1017 the whole way. We don't translate that because we don't have a rule, right? So that ping request, or that request to connect, comes from the data collection app to the HMI machine with an untranslated source address, and the destination has been translated, so the HMI machine receives it and it has the right MAC address. It says, okay, somebody's trying to ping me. I don't know how to get out of my network. How do I get out of my subnet? I'm going to now ARP for my gateway. So I'm going to ARP for the gateway. So now we've got both IP addresses in the ARP request. It hits the IE switch, and we're going to translate both of them, okay? It goes as far as the zone level switch. We've translated both those IP addresses. The gateway will respond to the ARP with its own MAC address. So now the HMI machine receives the gateway. We will fix up the ARP. Again, we talked about there was a couple of components there where we're doing fix-ups. We'll fix up that ARP, and now I can respond to that ping, right? So the HMI machine now says, okay, I know how to get to the destination. I'm going to forward it to the MAC address of the gateway. So we'll go through the NAT. We'll NAT that ping response. Now we don't have a rule for the destination. We keep the destination IP address the same. We hit here. We've now translated the source, so the HMI machines, and we hit here, and now it comes through. And now because a layer 3 forwarding decision was made at the zone switch, now we're changing MAC addresses as we get out of the layer 3 decision. Fundamentally, this is how it works on a layer 2 NAT device. Again, we're talking Ethernet switching. If you're hoping for something more complex, right, it's not there. So this is pretty the basic part. If someone is unsure about how that worked, now would be a good time to ask for clarification. Yes, sir. A brave soul.
That stupid device behind everything on the HMI.
Yeah.
The default gateway is that way of that controller, dual connected control. But I'm looking for 192.168.1.1.
Yeah.
That fine for this scenario, it works perfectly fine. But if that HMI machine really needs to communicate with that .1, then this IE L2 NAT switch, basically, it can't compromise all time. This NAT translate that ARP must sometime he has to return the real MAC address of that controller.
So if you're talking about going back a couple of other slides where there was a controller in the machine that was in the same subnet. So again, you have to realize the machines have pre-built software and static MAC addresses, and all the components in there know their own the IP address. So the HMI already knows that the IP address of the controller is .2 actually. So I didn't give the controller .1 on purpose, right?
It's configured in the way the controller, the HMI, knows the gateway as that controller.
Okay, the controller is not the gateway. The controller is just controlling the machine. It's not the gateway for the subnet. Because it's not a router or a switch. It's just controlling the machine. I gave it the 192.168.1.2 IP address because it's not doing any kind of gatewaying of any sort outside of the machine. It's just a component within the machine.
Okay. Because I understood that the gateway is already predefined in HMI.
Yes.
From the vendor.
Okay, so yes. You're taking the example very literally, which is fine. I'm trying to be more figuratively doing this to try and provide an example of how the layer 2 NAT would work. Every machine is going to be different and unique. When I get involved with the customers on these, it's almost always some different way of trying to do it with different types of machines. It's always something that's really old, that can't be changed. This is really what we're talking about. Can't be changed, and so the network just sort of has to adapt. Yes, sir?
On the you have to do each individual map.
Yes, and we're going to get to that. I'll show you how to do that in a little bit. Yes, but it's just easier to understand at this point by just thinking about a single host and a single translation. But the question was, can you do a mapping, a subnet mapping, rather than just an individual host mapping? And the answer is yes, and we're going to get there. Any other questions at this point? Because at this point we're going to sort of assume that we got the translation part and we're going to move on to something else. Okay. So we talked earlier about the permit all and the fix up all. These are relevant, and I'll show you just a second. So the first one is permit. The permit command is a very blunt instrument that you can use to control packets coming in and out on that interface and that VLAN that you assigned the instance to. It pretty much acts like as a deny ACL. In this example, I did a permit all, so I let everything go, but you can see you can just permit just IGMP or just multicast, but also you can permit unmatched, or you can deny unmatched. So if I don't have a translation for that host, I will drop that packet right there. So as it comes in, it doesn't have a translation, I will drop it. And if it's trying to egress, I don't have a translation, I will drop it. Very powerful. I say be careful when you do that. You've essentially put a deny ACL on your component that's outside of your switching infrastructure, right? So you'll be trying to make forwarding decisions in your switching infrastructure, and you have this other deny ACL that's not showing up in any of your ACLs in your switching thing. And so, but sometimes it's relevant. It has its use, and I'm going to post a video to our YouTube channel on how to use it correctly. I don't have an example here. Anyway, other thing is multicast. So CDP, STP, LLDP. If you don't permit multicast, all those get dropped. So if you're using some protocol that uses multicast, so be careful. I like to just say, my recommendation is just permit multicast. The other one is fix up. So in this case, the previous example, we used ARP and ICMP, so we fixed up both of them. If you want to block ARPs, one thing is do not allow them, or if you have a security rule that says don't allow ICMPs, don't fix those up. They won't go through. So it's one way to do that. Okay, so let's look at a different way to sort of solve this problem, right? The gentleman in the back brought this up. One of the issues if we're just doing layer 2 only on the IE, if we only had one machine, we would really have a problem. But if we have multiple machines on the same VLAN, we have a broadcast gateway, broadcast storm issue, where we're going to have duplicate IP addresses on the same VLAN, and that's never good, right? So it will look something like this. If we have VLAN 3004, on all these machines, the IE switch within each machine is connected up to the zone level. We have essentially got a duplicate IP address going across the network. This is fundamentally the number one issue why you would have this, right? So we've got, before we had everything on the same VLAN, we were talking only to the controller. The controller has a unique IP address, but now we're going to get access to the components in the machine, and now we have duplicate IP addresses. Hence, we need to bring in layer 2 NAT. So there's multiple ways to do this. This is the way that I have found to be the easiest to configure and get customers to transition to. There are multiple ways to do this, but this is one way to do it. As the network administrator, you have control over what the VLAN is coming in and out of the machines. So earlier we used VLAN 3004. Now we're going to change and we're going to use VLAN 100. So now we have different VLANs between the two. And at this point, you really don't even care what the VLAN is inside the machine. You may have to know it for configuration purposes, but it really doesn't matter. But we have this different VLANs for public and private. And every machine that we have, I'm not showing all the machines, but machines 1, 2, and 3 will all be on VLAN 100. So we changed the configuration to look a little like this, with a slight configuration change. One thing to note, now we are doing different VLANs here, as stated earlier. And the other thing that we're going to do differently from the previous example is now the layer 2 NAT IE switch is going to route. So now it's the gateway for 192.168.1.1. This is more of a realistic example, so I find. So now it's the gateway. You'll see we have these IP addresses here. We've also given, because it's routing, it now needs an IP address on the public IP network. So we've given it one there for VLAN 100. And we have one less translation to do. So we've removed that from our instance definition. So that's the big change. So if you wanted to look at your ARP table real quick on the switch, you would see that it's got a couple of its own IP addresses, and it has learned the VLAN 100 and 3004 IP addresses that way. If you're doing any kind of routing, it's sort of simple or nice to check that you're making the right IP addressing and MAC address learning on the right interfaces. So let's go through our build slide here to show how it would be different. Again, we're going to start with the same request coming from our data application. It will, of course, go to the gateway, the layer 3 gateway. It comes in. We're going to NAT that request because we're looking, again, the 10.0099. We have a translation request for it. But note that the destination MAC address is now the Ethernet switch, not the HMI. So this is a big change because we're routing now. So the MAC addresses are going to change. So when it hits the Ethernet switch, it comes with this translated IP address. The Ethernet forwarding decision sees the destination IP as 192.168.1.3. It says, oh, I got to change the VLANs on that and route it there. And now it changes the source MAC address for its own and changes the destination MAC address, which we just saw in the ARP table. Right? So the next part gets easy. Again, the configuration for the HMI device hasn't changed. The gateway is still 1.1. It ARPs for it, but now there's no NATing for that because it didn't actually have to go through the NAT translation because the switch itself is routing. It replies. And now when it responds back, right, we've got, it's coming, so now with the response comes here, now we're routing it, so the source and destination MAC address change. We go through the translation, we change only the translation right for the HMI device, and we forward it on. So this is, yes, sir.
If you're having a good gateway, what's the advantage of doing this?
You can actually, good question. We're just trying to show a different way. You can actually do this for multiple machines. So right now I'm showing the IE switch in the machine. One way to do it is you could actually, oftentimes you're connecting these machines to a switch. You can actually do this on multiple machines, so they're all connected together, and just doing the NATing there. In other cases, the IE switch at the layer 3 zone level, you can actually do NATing, this layer 2 NATing on the downstream interfaces. So if we go, so some of the IE switches supported on that layer 3 zone switch there, we could have done the NATing on each of the interfaces from its VLAN 100 there on the downstream interface. Again, so I referred to earlier in the presentation, different IE switches do layer 2 NATing on different interfaces. So on the 19-inch rack mount versions of the industrial switches, they NAT on the downstream interfaces. So you could have done the NATing there. It just depends on the configuration, deployments, what kind of products you have access to in terms of what you can do. Sometimes you can put an Ethernet switch in the machine. Sometimes you have to directly attach it to the machine. Yes, sir.
In this case, what is the difference between L3 and L2 NAT?
I know. Good question. So the question was, what's the difference between L3 NAT and L2 NAT if we're routing? Well, one thing is we're still not doing PAT. So this is not a 1 for N. So you could not set up a 1 for N type scenario. We actually made the routing, because the components are different between the forwarding decision that's being made in the switch and the NAT translation itself. We actually made the routing decision and then forwarded the Ethernet frame to the interface, and then the component translated it. From a black box perspective, it looks very much the same, but in actuality, it's not. It's actually, it makes a. But I could see, yes, there's some confusion there. But this is only one way to solve this, using making it layer 3. We could have tried to do this by doing the permits. So earlier we just permitted all, and we had a sort of a broadcast storm on 3004. We could have blocked unmatched packets, for instance, right? And kept everything at layer 2. That's another way that we could have done this, right? You look skeptical.
For me, it looks like L3 NAT.
It does. It looks a lot like that, yeah. Anything else? This is just another way to do it. I don't really have, it's only a 45-minute session. I can't just go through, I couldn't just do scenario after scenario after scenario. Besides, that would be boring. It's probably boring enough. It's tough looking at packets going through an Ethernet switch. Boy, talk about thrilling content. Anyway, so any more questions on the layer 3 portion of it? Okay, so now what we have is a zone level switch. So let's go back up. So to the gentleman's earlier question. So now how do I get rid of this, my duplicate IP addressing problem? So if I route on the switch, I no longer have a duplicate IP addressing problem, because the only packets that are being coming out of the machine are translated. So to save some cabling, I could probably do something like this: remove the connection from the controller and put it onto the machine itself. Again, so we have this is VLAN 100, and if it doesn't have a translation, right, so it's just seeing 10.0.0.100, this can just be layer 2 switched, right? So not everything going into this uplink here, it's not layer 3, it's still doing layer 2. If this is already on VLAN 100, we're just going to layer 2 switch it through the same interface. And it doesn't have an entry, so 10.0.0.100 doesn't have a translation rule. We're just going to forward it through untouched, right? So not everything has to be translated. And if we had say this is a trunk interface, if there were other VLANs that were on this particular switch, other than VLAN 100 or VLAN 3004, they would just be layer 2 switched as well, not translated. All right, so can I make it work in a ring? So in industrialized environments, we often see things that are done in ring topologies. It's often done mostly for redundancy purposes and to save cabling. Right? We can't home run or do a star network to everything because it just costs too much money to run a cable from every device up to my gateway. So the question is, if I have a ring, can I make this work in a ring? Can I do layer 2 natting in a ring? So, of course, I wouldn't present this if you couldn't actually do it, but it's not intuitive to some people. So I've changed the VLANs around just to keep showing the VLAN ID itself is irrelevant to this working. So now we're using VLAN 200. And we're doing pure layer 2 here. We're not doing any layer 3. It's a pure layer 2. And as long as you have a rule for every host that could potentially get onto the ring, and you have a rule for translation for every potential host, and you've applied the layer 2 NAT configuration to both of the uplinks. So you'll notice all the IA switches in this example have the translation on both of their interfaces. So you can put it on multiple interfaces. Again, it's not context aware. If the component doing the translation sees the packet, has a rule for it that matches it, translates it. So it doesn't really matter what happens. So the question is, what happens if a packet comes in from the network on the public and hits and it translates it, but it's a broadcast packet? So what happens if I have a broadcast packet that comes in for this device, we translate it, but it's a broadcast, so it's going to go out? Will the private IP address be sent out? No, that doesn't happen. Good question, though. I know that was the question you were about to ask. That's a good question. The answer is no. Again, because the switching component is different than the translation component. So it'll just be translated twice. So the broadcast packet will come in with the destination IP address of 1.3. So it will come in with its public IP address. We'll translate it, but it's a broadcast packet. So we'll ship it out this interface and translate it again, so that the public IP addresses only appear on the ring network. So you'll only see public IP addresses. No IP address conflicts are going to be seen because only the publicly unique IP addresses are on the ring. So if you are doing rings, it'll work with STP and rep. Again, those are done in iOS. Those are protocols in iOS that are maintaining forwarding states for the interfaces that are on the ring. Has nothing to do with the layer 2 NAT. So anything that will do forwarding information doesn't get impacted by layer 2 NAT configuration or vice versa. The only thing you have to do is you have to have all IP addresses that are on the ring have to be unique, or you will get duplicates. All right. So the question that came up earlier was, what about, can I do networks? Which I say, it's like I want to do all of the devices.
Excuse me, one question.
Yes, sir.
HSR also supported the ring?
No. Sorry. No, because actually HSR is actually done in the same hardware component that is doing the natting. So we have an FPGA on the switch that does the natting, the layer 2 natting, as well as doing HSR, and they don't work together. Okay, so if we want to do, if we have a whole network and we don't want to have a whole bunch of host rules, we can do a network. The smallest network that you can do is a /28 or 16 hosts. That's the smallest that you can do. The largest that you can do is a /16. So that's thousands of hosts, all with one rule. So you can do it this way. But the other thing that you have to look at is the masking that gets done this way is, I'm going to use this example. This is the most common one, was we're going to use a /28, which is 16 hosts, and that has a mask that looks like 240. If you're really doing like your hex, you'll know that we're really talking about only the last nibble is going to change. So in this particular case, I'm going to take the same sort of translation that I had before and mask it this way. And so it will actually go to, so 1.5 now, because I'm translating the whole subnet, 1.5 becomes 10. In this case, I've changed the IP addressing here, 10.10.0.5. So what would I do for machine 2 and machine 3 if I'm doing networking? So now I have to, again, the public has to be unique. And I have the mask of the /16. So I got to start each public IP address with a unique mask translation. So I'm going to go 16 and 32. So even if I don't have 16 devices to be NATed, the minimum I can do is 16. But now what happens is, again, I'm only doing the last nibble. This is the interesting part, is 1.5 in machine 2, right? 1.5 gets translated to 21. So 5 plus 16 is 21. So a little kooky, but if you know that's coming, then you can do that. Does that make sense? NATing machines? Okay. We also have the ability to use, besides the network instance, we also have a range, so you can give a range inside from range such and such to such and such, this way, and then with a mask. You can use a range command as well. Anything, questions, concerns? Rock. Okay, if you're going to troubleshoot this, one of the things that we actually are capable of troubleshooting, and we do a pretty good job of this when I explain to customers how to make this work, I encourage them to use the ability to look at the statistics. You can clear the statistics. So what happens is it's a very iterative approach when you're building your NAT rules and trying to figure out what's working, what's not working, and how you apply it. So you can clear the NAT rules and then send your sample traffic through. And we're counting everything. We can see, we count everything that we came from the inside, that hit our inside rules or our outside rules. We're actually translating, we're counting ARPs and pings separately, so you can see those separately, how those are coming through, what's matched, what's unmatched. So you can actually see how many are on that VLAN, so that came through that weren't matched at all, but just came through anyway, or matched or unmatched. So this is pretty valuable. One of the things that I like to do when I set this up is I pretty much just use pings. It's really tough to sort of get an external traffic generator in there to generate the right IP addresses that you need. It's really easy to use ping, to just ping through and test your translation. All right, so let's wrap this up. So one of the things is what we're trying to say is that oftentimes these things are done on purpose. You're getting a machine. You, the network administrator, are handed a problem where I need to communicate with the devices in this machine, and I'm not changing the software, and I cannot change the IP addresses, right? You, Mr. Network Administrator, solve my problem for me. Figure it out with the least amount of money, right? Of course, right? And one of the things we like, so oftentimes we find there's already an Ethernet switch in the network, so you don't have to buy another device. Oftentimes if they're asking you, well, can we make the current one work? So oftentimes this is often an opportunity, I don't know if you're looking for this kind of opportunity, to upgrade the network, because now they've handed you a problem, the current network can't solve it, you have to put a new device in there. So now this is okay. You can turn this sort of problem into an opportunity. Never miss an opportunity to something like this. Okay, let's upgrade your network. You need more advanced components. This unmanaged switch that you have here now is not going to cut it, right? It's time to put some managed switches in here with some features that will allow us to manage and maintain security, right? So now you can start having security conversations, as well as we have this need to digitize and start, getting processes enhancements. So this is a pretty common thing in industrial networks. The configuration guide that we have is pretty good. If you're familiar with the connected plant-wide Ethernet, which is a joint architecture document between Cisco and Rockwell Automation. So Rockwell Automation, if you don't know, is sort of one of the market leaders in industrial components, industrial solutions for all things automation and industrial automation and related. Anyway, so we jointly work with them on the solution. And also, and so in my team, I'm in the Cisco IoT business unit, and we have our own YouTube channel for all sort of our industrial components. You will find a very similar but shorter version of this already there, on there about how to do layer 2 NAT. It will be very similar to the one I just delivered, but much shorter, with more to come. And remember that this is a switch, and we're not doing port address translation. So that's it. Additional surveys. We have more industrial stuff to come. If you have any more industrial questions related, we have a nice setup down in the World of Solutions. Come see us. Labs and stuff. More industrial products on the way. We have some really nice security solutions. If you're looking at how industrial security is being implemented, we have a really good industrial security solution that's really grabbing everyone's attention. All right, 5 minutes early. If you have any questions or concerns, I'm gonna stick around. Anything related to industrial switching doesn't have to be layer 2 NAT. We're more than happy to help. Thanks you guys for coming very much.